we're going to start to get into how Bayeslands then extends upon what Badlands can do. So Badlands is great, but it doesn't give us any estimates of error or things like that. So we can put in parameters that we think are right and test a whole bunch, but Bayeslands essentially lets us test thousands of scenarios and will give us an estimate for how wrong or right we think we are. So are there any questions at the moment? Everyone's comfortable so far? Badlands, easy, fantastic. So let's move over to Rohit, who's going to give us an introduction to Bayesian inference and everything like that. Are you ready?
In 5 minutes. 5
minutes?
Yeah. They can play with Badlands.
Okay, yeah. If you just want to take like a 2-minute, 5-minute break or something, because this will be a bit of a lecture that's taking place. So at 1:35, we'll start it. Of slides here. These should be in the container as well. I think this is actually our whole bit open. Should be approximately.
Can I just ask? I installed the container on the other night. Do I need to reinstall it? Oh shit. Oh no. Oh, this is the final reason. Because the way I will give you a name. I'll read it. Is there a whole new? But then what happens? Yes, like I could write down. Yeah, exactly. But the insurance because the two lists are here. So basically, you just another list. Think about zero. Let's just go down. Oh yeah.
Okay, shall I? Thank you, everyone. Shall I begin? Okay. My presentation today is on Bayeslands, and when I made this planned this workshop, I sent an email around about Bayeslands workshop, and there was some guys in social media, they were sharing, what the hell is Bayeslands, you know, and one of these guys, he gave me a snapshot of that. So I thought, yeah, this is something, you know, this is something that can become very popular in the future, and I hope that it does. And this is basically, we are building up on Badlands. We're trying to provide uncertainty quantification and estimation of parameters. And I know a number of people get overwhelmed when they hear about Bayesian inference, when they hear about optimization. And a number of people have been working mostly in modeling in earth sciences, and they do not have the time to really think about optimization or inference, because these models take so much of time. And this is why I see that there's a huge research potential in this area. And I'm a University of Sydney fellow, and when I came to know about these things, I thought, let me put my other work aside and just get onto this. So I'm also based at the School of Geosciences here, apart from being affiliated from EarthByte Group and the Center of Translational Data Science. Nathan, how do we move this? And next, what do you say next?
It's a good question. Left and right. That should do it.
Okay. So moving on, basically we know that there are a number of free parameters or unknown parameters in models, and these models range all the way from in areas in machine learning and artificial intelligence. For example, a neural network is a very simplistic model. And in earth science, there are a number of models, and what we have been used to are Badlands, PyReef, for example, and I have heard about Underworld and kind of know about what Underworld does. So these are some of the known models, and they all have from a dozen. They could have a dozen to thousands of parameters, and the problem in geoscience is that data is usually sparse, limited, or incomplete, and the search for parameters in these models, we know you could use a number of optimization algorithms, but the major challenge is that a number of these models cannot use the standard optimization strategies that use gradient-based information, because gradient information is difficult to obtain. And moreover, evaluating a single model could be very costly computationally. Hence, there's a scope for using non-gradient based approaches, evolutionary algorithms, other optimization algorithms, and so on for optimization. However, there are challenges in optimization as well when the number of parameters increase drastically, and there are also limitations when we look at uncertainty quantification. So optimization is all concerned about getting the best or the near best solution, near optimal or near optimal solution, and it does not really cater for uncertainties naturally, but you would have to do a number of experiments using optimization algorithms to quantify uncertainty using a frequentist approach. So basically, running experiments, let's say 50 times, and getting mean and standard deviation, and then having some sort of confidence interval around it is known as frequentist approach in statistics. So there are two schools of thought, and then the others, that is one school of thought, and the other school of thought is called the Bayesian perspective or Bayesian methods. And rather than having a one solution through optimization time, 1 point estimate, they say, like, so you, rather than for that parameter, maybe a value of 2.2, for example, that represents rainfall, right? Maybe that is the optimal, maybe the optimal solution is 2.5, but you got value of 2.2, which is near 2.5. So you, rather than having that, what happens when you're using optimization algorithm, it all depends where you start from. And if you run 50 experiments, in each of them, some will give you 2.2, some will give you 2.3, some will give you 2.5, and 2.7, and so on. They will all end up at near optimal solutions. So the Bayesian approach is, rather than having 1 point, you kind of have a distribution of solutions. So you have a range of solutions, and basically you use a probability distribution to represent that solution. So in this example, where the rainfall of the values in the rainfall parameter is between 2.2 to 2.7, that is represented by a probability distribution. And we will move on and see how that is done. And therefore, people say that Bayesian inference is a principled or a rigorous form of uncertainty quantification. And just as in optimization algorithm, there are a wide range of algorithms that use gradient-based approaches and so on, which are very popular to kind of to provide Bayesian inference, or to implement Bayesian inference, you need to use MC-MC methods. And MC-MC stands for Markov chain Monte Carlo methods. And there's a wide range of algorithms in MC-MC methods. So one is the canonical MC-MC random walk sampler, whereas the other is parallel tempering, and so on. And we are going to cover both of these. So when we refer to, when we say sampler, basically keep in mind the sampler will provide you the near optimal solution that the optimization algorithm will also provide you. So MC sampler is essentially a type of optimization algorithm, or more clearly an estimation algorithm that gives you the near optimal solution, and it gives you the whole set of points around that solution as well. It provides you a distribution. And in the geoscience literature, MC methods have been used in a number of areas, which look at forward models in different domains, such as inferring the sea level, sediment supply, and inferring groundwater contamination sources. So this is the very basics of Bayesian inference. Bayesian inference uses a likelihood that kind of tries to likelihood with a MC method. The likelihood distribution is used to capture the relationship between the model data and the parameters proposed. So here, as you can see, you have a likelihood, you have data, and you have some priors on the data. The priors the priors essentially, in the case of geoscience, for example, in Badlands, the priors for a rainfall distribution would be uniform priors. That means that you know that your rainfall values will not be negative. So that's a prior. So a prior is essentially information that you try to put it into your inference process, right? If you give some initial information without looking at the data, right? So a prior is formed just by looking at the model, and usually priors can also incorporate expert opinion. So Bayesian inference is basically provides a fusion of information from experts, models, and so on to kind of to update that prior belief into a posterior. A posterior, you could see it as what you attain after the sampling process. That means the distribution of your rainfall parameter. Whereas in optimization, you will get the value of the rainfall, which is, for example, 2.5. Through inference, you will get a distribution, which the mean will be around 2.5. And that distribution is called the posterior. Okay? So that's the difference from prior to posterior. And basically, the goal of Markov chain Monte Carlo method is to kind of adjust this prior. As you can see, this is the distribution. It looks like that. And then use MC and Bayes theorem, and then you get a posterior distribution. See, the posterior distribution is slightly different from, or much different from the prior. So Reverend Thomas Bayes is the guy behind Bayesian inference, but he was a philosopher, a theologian as well. So he not only did maths, but also wrote books about divine intervention and so on, philosophical books back in the days. Very interesting guy. And there's the other guy, Laplace, who is not really that well known for Bayesian inference, but a lot of work was done by him as well. So we see that this is the infamous equation. Basically, it shows you the likelihood, probability, evidence, and the posterior probability. We will go much into detail with this. Actually, here you can see that. So this is the probability of being true given that B is true, the probability of being true given that A is true, the probability of A being true, and the probability of B being true. This is the posterior. This is the posterior, this is the prior. And we will go into more details here. For example, this is your prior beliefs, that's your posterior, and that's the evidence. The evidence is also known as the likelihood. So basically, your rainfall parameter, for example, for Badlands, you would have the prior is that so that's the prior, the black, and then the posterior. Yeah, blue is the prior. Sorry, you can't see, and the black is the posterior, and the likelihood is here actually. And with MC, basically you sample from the. They say that you sample from the posterior. When these are just the terms that are used. When they say you use MC to sample from the posterior, it basically means that you have some prior knowledge, you have your model, and then you are going to find the posterior. To sample from the posterior means to kind of find the posterior. So the likelihood, I mean, and theoretically or in a nice way looks like this, right? But the real world, we are looking at geoscience problems that have irregular surfaces and so on. And this is just the likelihood that surface that we obtained from Badlands for a continental margin problem that was shown by Nathan from the South Island. So let's not confuse ourselves with this likelihood surface and the actual surface of the Earth, that we use in Badlands. This is just a depiction of the surface where we have two parameters, erodibility and rainfall, and we are just trying to see what will be the likelihood given the combination of those parameters. And you could see here that there are a number of peaks, right? And which could be said suboptimal peaks. And if you kind of make a slice of this, then that is just the one-dimensional portion of it. And this diagram is looking at a one-dimensional view, whereas this is a two-dimensional. We're looking at two parameters here. So I know some of you are from various fields, and then it's hard to kind of visualize what a distribution is. And simply this diagram kind of shows you what a distribution is. Any series, basically, you get a histogram of any series, and that's the series here. You could see it as a time series. And if you make a histogram, that's a distribution, right? So we basically want to see which parts are the most, which numbers are the most likely. So what this is actually is just a visualization of the MC sampling process for just one parameter. And for that parameter, there you could see, you could imagine that the green point is probably the true value, whereas you are sampling around it and you get your mean value, which is 4, which is something close to the true value. So we will go into much details with MC sampling. Any question so far about distributions, visualizing distributions? Okay. So Nathan showed us Badlands example. What is Badlands? It's just Badlands is a landscape evolution model that is used to simulate topography development in various times and scales. This is the definition by Tristan. He's not here now, but this is written in all of his papers in the Python notebooks. So basically, you want to see, given a topography, how will this topography erode after thousands or millions of years? So, for example, we have this continental margin topography, and we see how it erodes after 250,000 years, and then 750,000 years, and 1,000,000 years. Actually, due to limitations in space, and also we are not showing the animation here, the Badlands model can show you the entire animation of how it actually erodes. And that's the beauty behind Badlands. But what Badlands naturally did not have is how to find or the values. For example, let's say that we want to find how the landscape in Sydney was formed. We have mountains, hills, and places, right? And we have some information that 10 million years the landscape was something like this, right? And we will need to plug in the right values for the rainfall value, erodibility, and a number of other parameters, the right values, so that when Badlands starts, like let's say 10 million years ago with the initial topography, it kind of produces at the end of the 10 million year simulation a topography that is equivalent to the modern day Sydney we have now. But to have that, to do that, Badlands should receive the right values for rainfall, erodibility, and so on and so on. And the Badlands model does not have that feature. So that is where that is how we kind of got involved. And then we proposed that we could use either optimization or inference. And then we weighed things down. Then we finally decided that we should have a inference approach to this, because with inference we'll be able to provide uncertainty quantification. And as you know, that if you go look at data 10 million years back in time, that data will be very sparse, the initial conditions and so on for Badlands. So it is good that the model parameters have uncertainty quantification. So basically that's Badlands. So how do we use Bayesian inference through MC methodology with MC sampler for Badlands? So this is just a depiction of the entire framework. Firstly, we have Badlands here, and evaluating one model as when we ran just before this took 7 seconds. It could take 30 minutes to 1 hour, and there are cases we heard could be a few hours even to run one model, right? So that means, and usually for sampling, we usually need at least 5,000 or 10,000 samples. So even if it is 1 hour per model evaluation, 5,000 samples means 5,000 hours. And that could be, I don't know how many weeks to a month or something like that. And hence, it is not viable to use it. Therefore, we changed the project, amended that this project and used something where we use high performance computing to do this. So let us first understand the basics here, because so with this we are just using a single core of the operating system or of the computer, and there's no parallel process running in here. It's just a single core, and you could just see this as a very simple procedure where you propose, let's say, a value for rainfall. You randomly pick, a value for rainfall and give it to Badlands, and let Badlands run for 1 million years in time. And then at the end, Badlands compares what is the simulated view of modern day Sydney versus what is the actual topography of modern day Sydney. And Badlands compares that these Bayeslands will compare the difference between them, the simulated versus the actual. And then with that difference, it will calculate a value in the likelihood. And the likelihood basically is based on the root mean, on the squared error, basically, on the difference between the two topographies. That's what the likelihood does. It's just a probabilistic framework, probabilistic way of capturing the difference in the simulated and the actual topography. So now you will ask me, why not consider all the simulated values for the 1 million years? The reason being,
Why not consider
yes, yes. So why not consider the difference between the simulated values of the past 1 million years? Because we do not have the, we do not know, we just know the present day topography. If you knew that information, then that information could be incorporated into the methodology. However, in this project, we did consider something else, and that is the sediment erosion and deposition, which is the sediment. So once when there's rain, when it rains, those mountains kind of erode away, and there's sediment deposition. And basically, in the real examples, you could have some data about the past millions of years of sediment information. That would be like, how many meters of sediment was in location A, B, C. So in some locations, you could have some sediment information for past 5 million years ago or 7 million years ago in the 10 million year period. Let's say you have just for 2 time scales. That can be captured by our Bayeslands, basically. So we not only look at the simulation versus the actual of the topography, but we also look at simulation versus the actual of the sediment deposition. Okay. So basically, the basic algorithm is, this is a very simple algorithm, and you will see the IPython notebook for this later. It is the main part of the algorithm is just a couple of lines. It's basically proposing something and then doing. So you propose a value for rainfall, for example. Let's say we're just dealing with one parameter. So you started with a, and so what is your prior here? Your prior, let's say here is that your rainfall value will be between 0 and 5, right? So that is your prior information. So you have a uniform distribution. Basically, you draw from a uniform distribution. Drawing from a uniform distribution actually means they're generating a random number between 0 and 5, okay? And the distribution there are a number of distributions. There's uniform distribution and normal distribution and so on. We will show this to you later. So you draw from that uniform distribution. Uniform means that the chance of you getting that number is, it is flat. Basically, it's equally likely. Whereas normal distribution, the chance of you getting a number around the mean is more likely than getting a number far away from the mean. So first you need to propose something, right? You need to propose somewhere, and that's what your initial values is, right? And then you draw parameter vector x from priors. That's what it means. And x could be rainfall, erodibility, marine coefficient, m and n. I don't know what that means. Only Tristan knows what m and n means, and a number of other things, And also, you could have your rainfall. You could have your rainfall parameter. Just one value of rainfall for entire Australia may not be the right parameter. You may need to divide Australia in a grid of like 1,000 points or something, so that instead of one parameter, you have thousands of values. But anyways, here we are looking at just one value, for example, and then you propose that. Let's say you set 1.9, and then it says that you propose a small perturbation to that value, and then you approximate. So you kind of put the random, add a random noise, and then you basically send this value to Badlands, and Badlands returns, what Badlands returns is just a simulated topography, the end of the 1 or 10 million years, that topography. And basically you would, in the likelihood function, you would make a comparison of the difference between that, right? And that you calculate your likelihood, we will go into the maths of each part into detail. So no worries there. I just want you to know the bigger picture actually. Okay. So we'll go into the maths of these. We'll go into the maths and even the code for these. That's all in our IPython notebook. And then you either accept or reject what you got. Accept means that accept or reject basically means that 1.9, if the likelihood was good, right? Likelihood was good. A good likelihood means that the value of likelihood was lower actually. Oh, I mean going towards positive number. So that's a good likelihood, which means that the simulated topography is very much close to the actual one. The difference is smaller. So that's a good likelihood considered. Whereas if the difference is much, there's bigger difference. Let's say, for example, in Sydney, there are 10 mountains, but in your simulated, in your actual topography, the ground truth, you have 10 mountains, but your Badlands produce only 2 mountains, right? So when you compare the 10 and the 2, you will have a poor likelihood estimation. So the chances of that being rejected, when it says being rejected, that means that the proposal that came in, which was 1.9, that will not become the current value. It will be kind of discarded. And if your current value was 1.5, that will remain as the current value. So you are going to do that and then repeat this step over and over again till a max samples has been reached, like for 5,000, 10,000, or 100,000 of the time. So that was a visual representation of the process. This is a very algorithmic representation of propose new values and calculate the acceptance probability and accept or reject here. So, but you can see this part in here is basically based on Bayes' theorem. To accept or reject the proposal, you kind of need to understand Bayes' theorem. And more on the problem formulation, the observed data is known as this fancy D. I don't know what mathematicians call it, but I would just say fancy D now. And this is basically Bayes' theorem. The probability of theta conditioned on the fancy D, you get D conditioned on theta versus probability of theta over probability on the fancy D. And basically going here, how was Bayes' law? So that is basically Bayes' theorem or Bayes' law here, right? Instead of A, we are calling it theta, and B here A we are calling it theta, and B we are calling it the fancy D. But how was this derived? This is derived from this. The probability of A given B, the probability of A given B with given the multiplication rule, a probability of A given B is probability of A intersection B divided by probability of B. So the A intersection B is same as probability of A multiplied by probability of B over A. Okay, so you see on top of your Bayes' theorem you have probability of this part basically, and this is how the Bayes' theorem, the conditional probability, is derived. So going into this bit here, basically, I don't know if you could view things there. Basically, here it says theta proposal, and below it says theta current. Okay, so basically, it's basically a relationship between theta, your proposal value for your rainfall, and your current value of rainfall, right? And relationship of them in relation to the likelihood. And how is that further derived? So this is what it is actually in that algorithm. and using the principles of Bayes' theorem. Basically, the top part is here, the top part, and the bottom part is here. And that same concept from the probabilities, basically this whole thing is on the top here and bottom there. But the only difference between them is that on the top you have the proposal, and on the bottom it's the current. So the theta is on top is proposal, and theta on the bottom is current, the C, okay? You can see the theta is proposal and the theta on the bottom is current, but the D, which is your fancy D, remains the same. And that is divided by the probability of the fancy D. Basically the fancy D, which is this denominator here, this thing, basically it cancels out. It cancels out, and then you're left with this, right? And I know that you may be wondering, then where is Badlands here in this formulation? Where is Badlands here? Then we kind of adapt this formulation by putting a G of theta instead of just theta, and that G theta refers to the Badlands model.
What part of the Badlands model?
No, it's the model itself, the governing equations, not the output of it. Yeah, the likelihood. It's from, yeah. Basically, this whole thing is the likelihood. Basically, the likelihood considers your theta that you have proposed, and it gives that theta to your Badlands. Badlands produces all that millions of surfaces, and the end surface, the likelihood again compares it with the ground truth data, and then gives a value basically. So this is basically the likelihood. Okay. Right. So that is just the simple approach of using a very simple MCMC random walk in sampling. Note that the simple MCMC random walk does not use any gradient information. When we say gradient information, so you see here on the top of the algorithm, here is a propose new value, right? You could propose the new value by taking some gradient information. Gradient informations are things that kind of are defined by the model. Maybe the model structure and so on. That is the gradient information that you get. So that the proposal that you give is in a better position. Going back to the gradient information, I know it doesn't sound good, but here, like what gradient descent basically does, like if you're traversing through this surface, the methodology that we have, we just add random noise to your current value, and then you basically move around this surface, right? And if you had gradient information, basically it gives you more details on where you should go next, right? So it's based on basically, you could imagine mountains and hills, and you want to find the lowest peak, or so the gradient information basically says that you are traversing down, and it's better that you take larger steps in this side of the hill, then you will reach there faster, basically. But the thing is, gradient information is available for models such as neural networks, right? Where we easily understand what the model is. But for complicated geophysical models like Badlands, we don't get that information.
Can I just ask, though, you were talking about having a random sampling, right? For example, rainfall, you say, okay, the minimum is 0. Do you set also a maximum? I assume so.
Yes, so that's what the prior does.
Okay.
The prior is minimum and maximum.
Okay.
So let's say that you have info, your prior at the moment is a uniform prior. That means there's a minimum and a maximum. But let's say that you had some more prior knowledge that you have more confidence that your main value will be around 2.5, you know. So that means you could use some other distribution, not a flat distribution. You could use a normal distribution that gives more information, or you more confidence that your value will be around that area. So that was our first part of the project. Then what we did, we moved on from that project to, because we had a number of challenges. The model that we were given by, the examples that we were given by Tristan, we cheated on those examples basically. We made a faster version of those things, you know. So, you know, things that taking one model, evaluating a model was like, for that Creta example was like 3 minutes in the beginning, and we turned it down to 1 second. You know, so instead of evolving it for 1 million years, we went to, you know, 50,000 years, and then the resolution factor and so on to reduce things, you know, and then we made that work with the MC Bayeslands basically. But we knew that that is not going to work out when we are going to look at bigger problems. So we thought, let's move on from here. So we finished that paper, submitted that, and kind of moved on from that and developed something called parallel tempering Bayeslands. And basically parallel tempering, you could see parallel tempering as your MC algorithm that is being executed on different cores on a high performance computing framework. Actually, in your laptop, you have 4 cores there, and with hyper-threading, you are given usually 8 cores. You know, so 1 core is usually divided. So you could imagine that instead of waiting for one MC sampler to end the task after 1 day, now you have 8 cores. So you distribute your task across the 8 cores. So instead of 1 day, theoretically, it is 24 divided by 8, the time. However, the parallel tempering is an approach where, while it is sampling, it's not that those MC samplers are run in isolation. Parallel tempering considers them to have some sort of communication between them. So that you could imagine it as that in here, going back to the surface, which is our favorite at CTDS, especially Sally likes it a lot. and actually Sally and Richard, they are at the Turing Institute at Oxford. And the team there, they really liked this surface because they are also a parallel tempering group there. And then I look at some real geoscience problems. And this one, they got really amused by it. So you could imagine that, let's say if it was just your MC sampler, it was just started here, right? It's just traversing all this way, and then basically in 5,000 samples, which was the maximum, it ended there. And then you did not really get a good solution. You did not reach your 2.5 value of rain is here, let's say in here. You did not reach it. You are still in value around 2, let's say, which is here, right? Actually, here the optimal value is 1.5. So you are around 2.5, and you did not get a good solution. Whereas parallel tempering, you will start here, there, and you'll start like in 20 or 30 different locations. And then you are going to, each of those samplers are going to communicate with each other, which likelihood is better, and some of them will swap their solutions. And then you are trying to get somewhere around near it. You see? So this is what parallel tempering is going to be useful for. And with that motivation, we developed parallel tempering. But typically, parallel tempering can be implemented, does not need to be implemented in the high performance computing framework. It can be implemented, a lot of people problems, you can implement it just for one core, basically. So instead of having a parallel, you can have a sequential version. And you could do that, and we did, that's how we started.
So essentially the communication prevents the different samplers kind of covering the same areas, wasting resources.
Yeah, with some probability, basically.
Are resources then reallocated to an area where the gradient is high?
So basically, we are traversing the space without looking at gradients. It's just, but you could imagine that the small noise, Gaussian noise that is added to the random walk, you could think of them as gradients of some sort. But we are not controlling that process. We just leave it as it is.
I guess maybe if you could get stuck in local minima and maxima, was that too strong?
Okay, this is great, so interactive session like this is great. Now it got you time to think without me telling you, So yes, those issues are there. Local minima, global minima, all those issues are, that's why parallel tempering is there. And the major component of parallel tempering is a feature known as the temperature, the tempering. So parallel tempering is motivated by principles in thermodynamics. So if you search the literature, do a search on Google on parallel tempering, you will see a lot of journals in physics published about parallel tempering, chemical engineering journals, astronomy. So it is something that's used across all the fields. So it is based on thermodynamics, which kind of says that when the forging process, when you go to people who kind of shape metals, you need to keep metals in a very high temperature to make maximum changes to the shape of metal, those metalwork guys. And when it's slowly cooling, and as it is cooling, then then it won't be able to make much changes, to the shape. You would have to really work hard, whereas in the beginning you just pound it a bit and then it changes the shape. So which means that the analogy here is that at higher temperature you accept more solutions that are not great, so you kind of traverse, you have a global search, and then at lower temperature you have a local search. I have another analogy for this, which I always tell my students. When you come to the university, I usually tell them, in the beginning, you kind of mix around with everybody, you want to know people. So, and you hang out with people, although you don't like them, so that you want to know them, So in the beginning, the first semester, you kind of mix around with people. And then after the following semester to the year 3, you end up kind of having a very small niche of friends. Why? Because in the beginning, you really explored, and now you don't, you cannot take it anymore. You just want to be with the people you like. So, but you did, to find these people that you actually like, you really explored in the beginning. Otherwise, you wouldn't have found them. So this is how the basic principle. So in the form of distribution, you could see this surface here. You could see it as a likelihood. So this is the likelihood. And what happens, basically, for each of those chains, the cores are known as a replica, or we call it chain or replica in each course, the MCMC sampler running. And for each of them, the likelihood is multiplied by 1 over t. 1 over t is the 1 over temperature. So what happens when you have a low temperature, your likelihood surface kind of looks, let's say, like this. But when the temperature is higher, the likelihood surface kind of flattens more, so that you could accept poor likelihood solutions, basically, more than when you will accept them at a high temperature. So you could see that you could get more trapped with the low temperature, but you can escape a local minima at a high temperature. Basically, your problem is same, but the way that each of your replicas are kind of representing the problem, that kind of changes. So that some of your replicas, so you could imagine that so there's something, the temperature ladder. So let's say that you have 20 replicas, and each replica has temperature 1, 2, 3, 4 to 20. So those replicas that have temperature, let's say 1, 2, 3, 4, those guys will have less likelihood. It's less likely for them to accept poor solutions. They are more for local search, whereas those with higher temperature, they are more likely to accept poor solutions. But after some time, I mean, actually in the canonical parallel tempering approach, so you make metropolis moves, basically. You make moves here, whether you accept or reject a solution. And going to the parallel tempering algorithm here, so you have algorithm 1, which is the normal metropolis Hastings algorithm that I showed you, MCMC. Then you have algorithm 2 that features algorithm 1. So you have the parallel tempering algorithm, you have the same way things are drawn, but you have all the different replicas from size 1 to m, so let's say 1 to 20. And then for each of them, you call algorithm 1, whether you accept or reject a solution. Then you propose whether you want to swap between the replicas. So some of those solutions between, let's say, replica 1 will be swapped with the replica 2 in the canonical approach. And we are using the canonical parallel tempering approach for swapping. So the replica exchanges, the solutions are changed only with the neighboring replica. But in the literature, there have been some implementations that the solutions are changed with other replicas as well. And they found that this works better when you are restricted by number of cores. We have less CPUs or less replicas, then it is okay. But if you have more replicas, then it's better you just swap between neighboring replica. And thanks to BGH, that we are given fair amount of CPU cores to do these experiments with more replicas. So basically, there's a similar approach is used here in the acceptance probability for swapping between the replicas. Just similar style used for accepting solutions within a replica. So you either accept a solution or reject a solution, or you swap the solution, okay? So these are just the two major steps, and you could visualize it mentally. So one major part is that how is the distributions created? So when you accept a solution, so basically, let's say you have 5,000 samples, and now you're using 20 replicas. So that 5,000 will be divided by 20. What is 5,000 divided by 20? 250. So each of those replicas will just do 250 samples each. So we theoretically, instead of 5,000 hours, we now have 250 hours of sampling. If one model took 1 hour evaluation, let's say it was an expensive problem. So what happens for each of those 250 samples, we will have a list of all the proposed values and the accepted values. We have that list, and that is basically this part of the algorithm is creating that list. If it is accepted, then you add it to the list. If it is rejected, then you just repeat the last part into the list. What was the last value that was accepted? So what happens when it is rejected, you are just going to repeat the previous parts, and that previous part was a better solution. That's why you rejected this guy here. And in that way, you are going to form a list of, you have a list of all your values for rainfall, erodibility, and so on. And then you make a histogram of that. That is basically your posterior after the sampling. What happens, the mean of that posterior, we take it as one of the, we take the mean of that list basically, and that we find, that is, we think of it as something as a near optimal solution. Okay. So in a distribution, like in a normal distribution, the mean, that list, you'll have that mean there. And that's your, and use that, plug it back into your Badlands, and then you will get a surface that is very close to the surface that you had. Okay. So basically these are all this way, so I kind of made you imagine more before showing you this. So this is the different temperature ladders and how the swaps are happening between them. And you could see this as 250 samples, and this is going all the way to 20 temperature ladders or 20 replicas, and in between the neighboring there's some swaps. But you see, this is not a canonical implementation. The swap is happening from temperature 1 to temperature 7, but not in our implementation. And then for each of those chains, as I said, the distribution. So this is after getting the histogram of that list of 250 samples. Let's say for chain of replica 1, replica 2, replica 3. So you have so many distributions here. You will have as many distributions as many replicas. What you do, you just merge them together. You add concatenate all those chains, and then you'll get one final distribution. This is, by the way, a multi-model distribution. Okay, so now I will take 10 more minutes to sum things up. So we created a synthetic ground truth topography. The way we did it, we had some initial conditions. The initial surface, for example, crater, and then crater after 50,000 years here. And then we have continental margin after then 1 million years. This looks like this. So we take this as the ground truth. Why? Because this is all simulated things. We are not looking at the real problem at the moment. We are, even the New Zealand example, we are considering it as a simulated case. And the thing is, the New Zealand, that example is of this time, for now. And we are evolving it after 1 million years from today. But after 1 million years, we don't have the ground truth. It hasn't happened. So we kind of evolve it, and then we take that ground truth as the actual. And from today, we assigned values in the rainfall, erodibility, and all the 6 parameter values, so that it evolved to this. And what are those 6 parameter values? We are giving it in this table, for example, here. All of them had rainfall of 1.5 m/A, and erodibility doesn't have something, doesn't have the type of unit, no unit value, M value, N value, and then we have sea marine and surface. But there's only, for one problem, there's another value called uplift, and you could see that here. And thanks to Nathan that this problem became possible. We had a lot of bugs when we were doing this. So this is a flat surface, and in this problem, there's another parameter called the uplift, which is, you geoscience guys know much better than me. It is due to mantle convection. There's plate tectonics, and there's, due to that, we have some form of uplift. So you could see that all of these guys have one value each, which is one rainfall value, which is, this is very highly reduced when you compare to an actual problem, because you have just one rainfall value, and we are considering that rainfall value to be used for 1 million years. But we all know that there's huge climate change, issues. So the climate has been changing every 1,000 years, or every few hundred years. That rainfall value should be different. But at the moment, we consider it to be the same throughout the evolution, and we also do the same for all of them. The other thing is that we know that in different regions, rainfall may be different, but we assume it is the same for all throughout the grid. So, and as I defined, that the model likelihood, it basically captures the difference between the simulated and the actual. And this is basically the maths behind it. And basically this kind of beautiful / ugly equations that you see, depending on your perspectives, or it is basically implemented in the IPython notebook. Basically, it's very simple. you could see, because why do we have these two sums here? You see the D and the F of the theta, this is what your Badlands produces. So you give it a theta, that means values of rainfall parameter and so, and it outputs you a topography, that's the simulated topography, and you compare it with the D, which is the actual topography. Basically, it's a subtracting two surfaces, point by point subtraction. And tau squared is basically a parameter, which you could say is a parameter that kind of considers noise in the model. And this whole thing is because we are following the Gaussian distribution, and this is the maths behind the Gaussian. So this likelihood is actually called the Gaussian likelihood. And for sediments, because for the sediments, we need to also consider the time information. So in our case, we considered 4 different sediments at 4 different times. So we arbitrarily picked some areas, and basically we looked at the height of the sediment deposition in this area at 4 stages in time, basically. And we subtracted them, the actual versus the simulated one, and we added this to the likelihood. So we have example where there is, where we don't use any sediment information, which is the mountain example, but in the others we are using sediment in time. So, so now comes the design of the experiments, the first set of experiments that use MCMC random walk. And this is just a visualization of the likelihood. And this was for the continental margin problem. And this is just for the crater problem that you saw, the relationship between the rainfall and erodibility. What these things say is that there is a combination of rainfall and erodibility that gives you the high likelihood. So sometimes you have less rainfall and more erodibility, that is equivalent to more rainfall and less erodibility, some combinations. That's why we see this peak there and a number of peaks. So this is just what we got for the rainfall distribution. And this is basically all the trace plot of how it was sampled during the sampling process by MCMC. And you see there's a number of lines in colors here, because those are just different combinations of rainfall and erodibility that gives a high likelihood, because it's a multi-model problem.
So the water plots are a sample number going across the x-axis, and along the y-axis is the value of that parameter. So it's like increasing or decreasing the value of the parameter and testing it. And the top plots are the parameters on the x-axis, and the y-axis is the number of accepted values. Is that right?
Yeah. Are you getting to this result?
Yes. So yes, exactly. Actually, so this is the trace plot. This is your basically the width of this. The width of this is basically your range of your search. That's defined by your prior. There's the width. So it's a rainfall value. It starts from around 1 and it goes all the way to 2.5. Whereas this is just basically a histogram. So basically this says that around the value 1.5 was accepted the most, 20,000 times in 100,000 times of the sampling.
That's one chain on the MCMC that can be parallel.
So yeah, we'll go into the parallel tempering results next. So the parallel tempering project the goals were a bit different. The Bayeslands MCMC was just to demonstrate how we can wrap this up in a framework and have some sort of inference and look at the likelihood surface, whereas the parallel tempering was about taking that framework, using it in a high performance computing environment with lots of cores, see how the time is reduced and the accuracy is improved. So we investigated on a number of things, which is how many cores should you use, what time should you run it for, and what does it produce like. So this here shows that as you increase the number of cores, and this was for the continental margin problem, I think, the time in number of minutes from 700, it goes to less than 200 minutes after 40 cores. Okay, and the accuracy is somewhat similar. We have an outlier here though. It's a bit difficult to explain this clearly, this accuracy part, because as you saw that Continental margin problem had a number of peaks, and it all depends, even by parallel tempering, we found that you could be not in that, the top peak is usually not found, even by parallel tempering. But that photo that you saw, that image that you saw of the surface, that was just for 2 dimensions, rainfall and erodibility, whereas we are looking at 6 dimensions, which cannot be visually shown. So it becomes a bit more complicated than that surface, like in a grand scale complication. So if you really want to know that surface, I would recommend you see Interstellar, the movie.
So what's the chance that you actually miss your maximum?
That you actually miss?
Yeah.
The chance of actually missing a global maximum is lower as you have more cores and more time. But there's no, quantified.
There's a lot of formulas in the models that adjust the temperature and things like that. You're more or less likely to find it. Sometimes you might miss it if you don't have as many samples, and it's likely that you
Is there a rule of thumb based on like number of parameters in a model, roughly how many samples you want to have?
There is no rule of thumb actually. I mean, so
depends on the surface as well. Like for example, on the Continental margin, we found that we needed a lot more samples because of the likelihood surface being so complicated and the maximum defined it. But for the crater problem, we knew that there were a certain number of combinations that would hit the maximum likelihood. So for that, we used quite less samples.
And the complexity of the surface relates to the number of parameters.
Not necessarily, because in the Continental margin, we use the same parameter as the crater as well. So both of those surfaces were just for 2 parameters, rainfall and erodibility. So it necessarily does not depend just on the surface and how complicated the surface is.
the surface is so complicated, as you can see. Our prediction RMSE, which kind of looks at the quality of the whole samples, when we have 1,000 parameters, it's 120 here. And then 2,000 is around 220, but then 8,000 is also around 220. So it doesn't matter at times, even if you have taken more samples, because the surface is so complicated, even taking less samples is almost similar to taking more samples at times.
It also depends on where the gene starts. Because
Yeah.
the gene can start at a very, like say, if you can show the surface again.
Yeah.
The chain can
Start here.
Start at a local minimum already, so it's going to struggle to actually get out of it unless the temperature is different. So for the parallel tempering, to go back again, for the parallel tempering, each chain has a different likelihood surface because the likelihood surface depends on the temperature. If the temperature is high, it's going to see less of those small peaks and see more of a flatter surface, and the main peak being a little more obviously reachable than when it's at a lower temperature. So this particular likelihood surface was at 1 temperature. So it depends on which chain starts. Whereas if the high temperature chain starts at the central point, so it'll be very highly likely that we get the maximum.
It's kind of hard to answer, but that global maximum is very concerned. Then why do you bother?
Well, that's because even at a higher temperature, the peak will become much more wider. Like it won't be just a center point. It will be like a wider round shape. And once you reach that point, then if that chain swaps to a lower temperature, then the peak starts becoming more obvious. Like that. So for example, in a higher temperature, the peak will be around the radius of that peak sort of is like let's say 0.2. Like it will be from 1.4 to 1.6. Like it will be just showing 1 peak in that. And when that same chain goes to a lower temperature, it's going to see that the peak is actually at 1.5 and not between 1.4 and 6. then it benefits from doing the micro search sort of.
Okay, I'll just quickly wrap this up in 5 minutes, and then we can have discussion.
Do you want to do some examples and come back to the results?
No,
Maybe I can run the MCs.
no, I just wrap this up because I'm too tired to stand here. No, it's fine. It's fine. I was just finishing. I'll finish. Unless you guys want the break. So we can see that it's a bit complicated situation here. We cannot have big generalizations about how many samples should be used, how many cores should be used, and so on. But in the grand scheme of things, we would like to use as many cores as possible. Okay, because you'll have the model will take 1 hour or 2 hours. You better use more cores if it's available. So we have a quick summary of the results here. As you can see, the time taken, we're reporting, and all these things are in the paper. So we have something, the sediment RMSE difference, elevation RMSE, and the prediction RMSE. Basically, prediction RMSE is combining sediment and elevation RMSE. So basically, all those differences in the likelihood, the two likelihood, we join them together. Yes, Tristan?
So by sedimentation, thickness of sediment is
Yes. So it is the sediment thickness. So it's a negative value, then it used to be considered as erosion, whereas it's a positive value, it's a deposition. So this is an example of one of those problems where we found like where it converged for the continental margin problem. And basically this is what we saw. This surface here is very much close to the ground truth, and it gives the view before that for the 4 stages of evolution. And this is just a depiction of the sediment deposition. So this is erosion, the bottom, and this is the deposition. And so you could see the green is ground truth and the blue is the predicted. And the pink lines are the uncertainties, basically. Note how is the uncertainties quantified. You could see that if you are doing 10,000 samples, you'll have this 10,000 times this thing, 10,000 of those predictions. And basically we add them all up and get the mean, and the blue thing is the mean, and then the credible interval or confidence interval / credible interval in Bayesian inference. They call confidence interval, credible interval. And that is the pink thing. So for all those accepted values, so each time this is another data issue, each time we accepted a solution, like a parameter, rainfall parameter, we also captured what is the sediment and what is the prediction in the topography. We captured that as well. So this is the same thing, but for the mountain problem. And we give a cross-section of the continental margin problem. So this is just like a cross, like a Easter bun, you see a cross on top, that type of cross-section. And you can see that there is the ground truth, the prediction, and 5th percentile and the 95th percentile. So this is basically, we did not save all the images for the topography part because our hard disk was just getting full. It will be like more than 10 GB, or it could be more. But we just saved the snapshot, so we wanted to show the uncertainties in the prediction. And this is basically the main purpose of Bayesian inference, that you have a natural way of accommodating uncertainty. And this is for the mountain problem, again, the Easter bun cross. And then you have this, you could see that the predictions are very much close to the actual ground truth, which means that we have found one of those suboptimal or optimal peaks in the rainfall or the erodibility. And this is an example. So you see here that we found that our inference process, the optimal is 1.5. That is what we use to generate the data, the ground truth data. But what we found here is around 2. So that is, we found a suboptimal peak, right? But if you see the prediction, it is not so bad. So even those suboptimal peaks are not really that bad.
It's because of the likelihoods of having like similar values on a combination.
Yeah, but this is this one is, because this one is not for that problem. This is for the continental margin problem. So the same thing in here for erodibility. But in one of them values, like our sea marine deposition, we find the true value. So now comparing the two papers, the best thing here, I should have shown a histogram. For the crater problem, we reduced our time from 136 minutes to 8 minutes. And when we used 100,000 samples, we reduced our time from around 1,000 minutes to 78 minutes. This is like a major contribution. And the continental margin problems greatly reduced as well. 100 minutes to 7 minutes and 700 minutes to 50 minutes. And the bigger contribution here we could see is that in our MCMC baselines, our sediment predictions were not really good. You could see a RMSE of 8, whereas in our parallel tempering, we see a RMSE of 4.2. And then you have a continental margin problem, you have a RMSE of around 400 something, whereas in our parallel tempering baselines, we have around 7. You know? So there's a huge difference in prediction quality, not just time. So, and the elevation RMSE is similarly drastically reduced, so that our total prediction RMSE for the continental margin became from 500 to 32. And the time became from 100 to 7, which is a huge improvement in this actually. And again, that figure. So basically all the aims and goals for the project, we fulfilled it, and this workshop is part of one of the other final goals for that this project. And we are moving on as well. We are developing Bayeslands with surrogate assisted likelihood functions. We want to reduce this time further actually. There's more opportunities for improvement. So the way we are going to do it, we are going to use a machine learning model like a neural network, for example, or a Gaussian process model that learns and tries to mimic the actual model. So sometimes you will not evaluate the actual model, which will take 1 hour, but you'll just evaluate a neural network, which will take less than a second or minute. So in that way, we are going to reduce that time. And Konak here has showed that for neural networks, and we are looking at 1,000 parameters, and we are reducing the time by half in the neural network approach, and we are submitting this paper by the end of the month. And Daniel is implementing that for Bayeslands. And that should be also, we're trying to finish this project by the end of the month or early August, and we will release it to our EarthByte friends. And this is what Sally is more interested in. She's interested in developing better methods, and this is one of the goals of her trip to Turing Institute. So also looking at if there's some way in which your proposal distributions, the way that you propose, instead of having a random walk, you have some graded information or some other smart ways to give that information. The other thing is that apart from the, once we have done with the surrogate likelihood, we would like to apply it to a real world problem. And we were having discussions with Dietmar, and Dietmar referred us to Sabine. We will have discussions with Sabine later for some real world problems. And then also we are looking at time-dependent uplift and time-dependent rainfall, and Nathan is taking care of that implementation with Tristan there. And probably by mid to end of August, we should be done with that. And basically, basically after September, I won't be doing that much of Bayeslands. maybe more applications. And so this one major part here is that our time-dependent uplift and our time-dependent, for example, rainfall. Let's say if we get time-dependent and region-dependent rainfall information for Sydney, we would basically have a time series, and that kind of helps us understand not just the topographic development over time, but makes us understand the climate patterns. And that's rich data that we're looking at, and we would like to show and demonstrate this for a real actual problem, so that with that data we can predict the future of climate. And the last but not the least, parallel tempering can be improved with optimization methods, gradient information, informed models, and so on. And we are giving it with this workshop and with the papers, we are giving the software packages, the libraries, and in the future, we would like to have a bigger library, that with all these papers that are coming about in a couple of months, we would like to have our own library that is released and used throughout Australia, hopefully. And thanks to our project members and everybody here. Thank you.